Hello everyone, in this video we are just going to start writing our own CMSIS structure program for the GPIO peripheral of the microcontroller STM32F446RE. Let's get started. So I hope you remember this program that we wrote, that is the simplest program of LED blink in the microcontroller STM32F446RE. So in this program we just declared and defined several register addresses using pointers. So these raw addresses are declared and defined inside a pointer, and using these pointers we just wrote values to the registers of the microcontroller. But in this video we are just going to alter this program to a universal standard called CMSIS Standard. So the CMSIS is nothing but Cortex microcontroller software interface standards. So this particular CMSIS standard is a universal standard followed by almost all the silicon vendor, that is the microcontroller manufacturers. So the CMSIS files are provided by the silicon vendor or manufacturer of the IC itself to all its suppliers, so that they can develop their own user applications using the particular microcontroller. But in this video we are just going to demonstrate and write down structure for our GPIO peripheral, and then we are just going to perform the same operation of LED blink and utilizing the structure that we are going to write. So as per the CMSIS standard, that is the universal standard, we are just going to create structure only for GPIO peripheral right over here, and later just try out with the same procedure that I am doing in this video for rest of the peripheral, so that you will get a very clear understanding about the CMSIS standard and structures that we are going to create in this video. So this is very important because almost all the ARM Cortex-M microcontrollers follows this standard as per the user manual of the microcontroller. So now I will unleash the user manual of the microcontroller for getting the details required for creating our own structure. So first and foremost information that I want is the base address of the peripheral that I am going to create. So before that I just want the peripheral structure, so that you can find in each and every peripheral chapter itself. So I just want to create the structure for the GPIO peripheral. Just click on the GPIO tab right over here, click on the plus and then click on GPIO registers. Click on the plus near the GPIO registers and come to the last section, that is GPIO register map. So when you say a particular standard, that standard must be universal, right? So whenever you create a particular structure or universal file for any microcontroller, there must be a particular standard. So that particular standard is dependent on the user manual of the microcontroller. So this is the user manual. So in this user manual we found this GPIO register map. So the structure elements must be in this order, starting from GPIO mode R, second register is GPIO type R, third is GPIO speed R. This is the way of showing that this GPIO speed R can be utilized for any registers from A and H, and also it can be used for GPIO B, etc. And next register is GPIO PU PDR. It goes on like this. So this must be the order for universal convention. So by using the register map page in the user manual of each of the peripheral chapter, you can define your own structures for any of the peripheral of the microcontroller. So now what I will do is I am just going to comment all these GPIOs. I don't require this. Here I am just going to declare my structure. Let me just provide the name for the structure to be GPIO definition. And as I mentioned, the elements of the structures are registers available right over here. In the same particular order, you can clearly see this GPIO mode R is the first and foremost register in the GPIO peripheral of the microcontroller. So this register map is the thing that describes the order of registers in a particular peripheral of the microcontroller. The first and foremost register is the GPIO mode R, which is available at the offset of 0x00 of the peripheral. So let me just declare this first, GPIO. So I will just declare it to be mode R. So what should be the type of the element declared? So this can be decided based on the size of the register. You can clearly see it starts at offset of 0x00, that is the mode R register starts at offset of 0x00, and the next consequent register, that is the type R register, starts at the offset of 0x04. So I just want to provide a size of 4 bytes to the mode R register. So it can be int, or to be particular you can use another default data type uint32 underscore t, which is 32-bit integer variable, unsigned integer variable. So if you are getting unknown type name, just include this header, that is the standard header of stdint.h, so that this error will be ignored. And the next register that is available consequent to the mode R is type R, uint32 underscore t type R. And the next register is speed ER, which is available at 0x08, uint32 underscore t speed ER, uint32 underscore t. Next register is PUPDR. So this is available at 0x0C, and the next register is available at 0x10, that is IDR. The next register available is ODR at 14, that is the consequent 4th byte. The next register is BSSR, available at 18. And the next register is LCKR at 1C. And the next register is AFRL at 20 and AFRH at 24. And that's it. So this is the peripheral structure that we have created as per a universal standard, as per the user manual of the microcontroller STM32F446RE. So while declaring and defining elements of the structure, make sure that all the registers are available in a consequent memory location. That is, the first register is available at the address of mode R, and the next register is available at the address of 04, and the next is available at the address of 08, and next is available at the address of PUPDR, etc. It must go on like this. If you are finding some gap in between any of these two registers, let's take an example that this IDR is available at an address of 0x10 offset, and this ODR is available at an address of 0x14. So let's take an example that this is available at an address of 24. Then there is a huge gap between these two, right? So those gaps must be filled with dummy variables inside the structure. So make sure you do that. So the amount of space, let's take it to be 4 or 8 or even 16 or even 200 300 bytes, must be filled with reserved variables or buffers. So make sure you do that if you are facing anything. So I am doing and writing the peripheral structure for GPIO peripheral of the microcontroller. So in a similar manner, just try out and create your own structure for RCC peripheral of the microcontroller. I will not be altering these two. You just want to perform the same operation and you just want to create your own structure for this RCC peripheral of the microcontroller STM32F446RE, and I want you to alter and see in the same program. I'm not going to alter these two segment, this one, this particular segment and this particular segment. I'm just going to leave it for your scope. You just want to change this by writing and creating your own structure as per the user manual of the microcontroller STM32F446RE. So we successfully declared GPIO peripheral structure. So now I just want to find the base address of the GPIO-A. So coming to the memory bus architecture, memory organization. You can see in this table register boundary addresses, you can find the GPIO-A is available at the base address of 0x40020000, and GPIO-B is available at the base address of 40020400. C is available at the base address of this one, D is available at this one, E is available at the base address of this one, and it goes on like F is available or having the base address of this one, G is having the base address of this one, H is having the base address of this one. So whatever the GPIO port that you want to configure, structure remains the same because the register structure of the GPIO peripheral of the microcontroller is same. So only thing that you want to change is the base address of the GPIO port. Since I am going to configure the GPIO-A, I am just going to declare and use the pointer for this base address. If you want to do the same for GPIO-B, just use the base address of this one. That's it. So this makes the CMSIS code more compatible. That's it. Just change the register base address and you will be able to access the set of registers for the particular peripheral, keeping the structure common. So this is the common structure for GPIO peripheral. So now for loading the base address and using the peripheral structure for GPIO-A, I just want to declare a pointer for GPIO-A with the base address of GPIO-A peripheral. So this is the base address. Let me just copy this. So this is the base address. So what I will do is I am just going to declare pointer and name it to be GPIO-A and load this pointer with this particular base address. So the warning that has been shown right over here is the type conversion incompatibility. So it is telling like this is an integer value, it is not an address, but this is a pointer. You just want to load only the address to this pointer, not a particular integer value. So I just want to convert this value into respective pointer or address. So for that I will be converting this into pointer of GPIO def. That's it. So now what happens here is the GPIO-A has been loaded with the value of this one. So this is the base address of the GPIO-A pointer. So it starts with mode R. This will be the starting address of GPIO-A, and this will be the starting address of this type R register, and this will be the starting address of this speed R register, and following that this will be the starting address of PDPR register, and this will be the starting address of IDR register, and this will be the starting address of ODR register, and this will be the starting address of BSSR register, and this will be the starting address of LCKR register, and this will be the starting address of AFSR register, and this will be the starting address of AFRH register. Since we are configuring and loading the base address of the pointer GPIO-A of the type GPIO def, that is this structure type, to be this one, the register addresses will be in this manner. So whenever we use the pointer GPIO-A and when we write to this particular mode R, that data will be written in the address of this one. And whenever we use this pointer and when we try to write to this ODR register, that will write the data to the respective address of 0x40020014. So this is how it works. So now let us try to alter the program as per our need. So now what I will do is I will just comment out this. So what I can write is GPIO mode R is equal to 10th bit setting. So I can write like GPIO-A is equal to pointer pointing to mode R is equal to GPIO-A pointer pointing to mode R of 1 left shifted by 10. GPIO type R is equal to 0x0000. 0x0000. GPIO-A over speed R and here I just want to set the 5th bit of ODR register. GPIO-A ODR is equal to GPIO-A ODR R of 1 left shifted by 5. Here I just want to clear the same bit number 5. GPIO-A ODR is equal to GPIO-A ODR ampersand of 1 left shifted by 5. That's it. So in this manner you can use this pointer GPIO-A wherever you want for writing to the particular GPIO-A peripheral registers of the microcontroller STM32F446RE. So this has become a standard for us right over here. So in a similar manner you can also define a structure for, take it to be GPIO-B and provide the base address for the GPIO-B right over here. So that you can use this GPIO-B wherever you want to write to the registers associated with GPIO-B peripheral of the microcontroller. So just try out the same example with GPIO-B, connecting GPIO-B pin with an LED, and then try out to create your own structure for RCC peripheral of the microcontroller. I will not be doing it. You just want to try it out. Just keep in mind, just try to create your own structure for RCC peripheral of the microcontroller. I will just give you a hint. So in the same manner, just pick the RCC base address, that is this one, and then move to the RCC peripheral. This is a bit longer register structure peripheral, so that's why I'm trying to make you do it. You can see we just want to follow this register map table. This is having some larger number of registers. Just try out creating structure for this. You can see in this example, at the offset of 0x18 we are having AHB3 RSTR register, and at offset of 1C we are having reserved space, and offset of 20 we are having APB1 RSTR. So in this reserved space, just provide a dummy variable of 4 bytes. Or if you are having 8 or 12 bytes as reserved space between two registers, just provide a buffer dummy variable of so and so elements, so that this space will be filled in the register structure. So this is a hint that I'm giving for you, and then try to get this program working, that is the LED program working. I'm just comparing this. I'm just connecting my STM32F446RE development board to my PC, and I'm loading the program to the microcontroller. And you can see the LED blinking in my Nucleo F446RE development board. So we successfully created peripheral structure as per universal CMSIS standard for GPIO peripheral of the microcontroller STM32F446RE. So in a similar manner, just try to create your own structure for RCC peripheral, and I just want you to alter this program, this part of the program, and also I want you to comment out these two parts of the program. So I hope you learned the universal method for creating structure for peripheral of the microcontroller STM32F446RE. So in a similar manner, try to create your own structure for RCC peripheral after this video. See you in the next video. Thanks for watching.